Yeah, too warm of a response from me. Appreciate it, guys. Good morning.
Good morning.
Good morning.
Thank you so much. Everybody that is present gets a reading point. All right, I see that, let me see, Ethan Jackson is absent. Everybody else is present. All right, let me give you a reading point. Guys, you know that this Friday, school is closed, we're off. So no office hours for Thursday, no class for us on Friday. Remember that? It gave me a week. I'm going to take that long weekend to finish up your test grading. All right, so I will be posting your attendance and bonuses for Leg 2 in the coming days. So the only thing left for us is Leg 3, one homework left, one task left, and one project. The project, based on the team's input on Blackboard, I developed basically, I had to combine 2 or 3 of the teams, add more members to it, just because they were not able to follow the policy to have minimum of 4 members. So I had some of you ask me specifically, they needed 1 member, so I helped with them. I added those people to their team. And then I had to make I had to basically, I believe, delete 2 of the teams to really satisfy that minimum 4 members. So that's why 2 of the teams might see that, oh, the team is not there. That was the reasoning behind it, per the policy. The first member is the team member, the team leader. Again, if the first person is any of the 1 member of the team is part of the honors students, you want to get credit toward that, make sure I ask you, but assume you forgot, make sure you come to me after class, let me know so that I update that list and basically we're calling you an honor student so that I give you the bonus for that also. I mean, toward the honor program requirement, not this bonus. All right, so that's about project. Make sure you start early so that you do not fall into the full stress of the final week. So start early and resolve all the issues. Believe it or not, this is what happened before. People were just complaining of themselves. Why did they did not start earlier? So take advantage of it. Start early and come to me if you have questions. If you come to me, if you email me on 11th week, I'm not going to respond to you on project. You have all this time, take advantage of it, start early, and I'll help you as one of your team members. Even on the presentation, if you have ideas, come to me, you say, how should I do that? I'll help you. But do not leave it to the last minute. All the formulations, again, we did those as part of the session. Toward the end of our notes in Leg 2, we did all the derivation together. You just need to come up with the values for your bridge and then plug those into the equations. All right, that was about the announcements. Let's talk about the new topic. There are 2 topics left. One is rather short, the other one is really the crux of Leg 3. In fact, without that, this course would not be that efficient, that applicable. We want to make the course practical, and that makes it really practical. So beam deflection is something that you're going to see later in other courses, machine design, for instance. And stress transformation and principal stresses is what really makes the course practical. So bear with me, I'm going to go over each with a lot of examples. So the first one, let's go over that. As discussed, you need only this and this. The rest is really warm up and extra information. Make sure you do have at least these two, your equation sheet. So beam's deflection. So let's first define beam. Guys, geometrically, what's your definition of beam? What do you think? What would you call beam? Something a beam.
Like a pillar, like a circle, a cylinder shape, or shaped like a rectangle.
I saw your hand, and because of that gesture, I give you a point. That was actually the thing. Nathan?
A shaft of some three-dimensional shape supported at some point along the shaft.
You did not add anything more to what Jesus said. Nathan, please.
Usually a fairly long structural support.
That's the point. That's the point.
Which one?
So Nathan and Jesus each get a point. Nathan, if you do not mind. Yes, when we talk about slender objects, we're talking about beams. Whether they're connected or not, that's not the point. Okay.
Just beams.
So the bridge, for instance, are really long in one dimension. The cross section we don't compare whether it's circular, rectangular, square, or any other thing. All right, Jesus a point. Nathan Schaffner a point. All right, so that's beam. Normally, really we talk about long length compared to, let's say, dimension. So maybe 10D even. It's greater than 10D. So greater than 10D diameter, dimension in other directions. All right, so that's the definition of beam in engineering. So this side of the equation, so this models the behavior even. The behavior of the formation of beam under the application of load. So this is something we already looked at. Open question, guys. What's the name of rho?
Radius of curvature.
Radius of curvature. Several names for E. So raise your hand and get a point for that. First, Kiro.
Modulus of elasticity.
Yes, modulus of elasticity.
No, it's the same.
Okay. Stay with that because we have more. I'll give you a point.
Units modulus.
All right. The point to use? Yes, thanks. Elastic modulus. Yes. Jacob, Kiro, Max. I'm not sure if there was any other hand up or not. Yes.
Young's modulus.
Young's modulus. So you're rocking today. Yes, there's one more.
This is stiffness.
Yes.
Stiffness.
Jesus, very good. Stiffness. So any of those names is cap E. The slope of the stress strain curve in the elastic region. That's the line. All right. And then the parameter I, the big name, Drew.
The second moment of area.
Second moment of area. And it measures, no, somebody else, let's say. It measures
M of J. M of
resistance to
4.
bending.
You don't want the unit.
Drew and Point, Evan Mushler. All right, so we went over that. As a reminder, I for rectangular, give me the equation for that. I saw you first, yes?
112 base times height 1 and then cube, whichever was perpendicular.
You continue, please, Justin? Just so you did get your point. Yes.
1 over 12 times base times height when everyone's perpendicular to you, perpendicular to the bending axis.
To the bending axis, not to the force, not to anything else, right? To the bending axis. All right, just a point and Josiah. Yeah, Josiah, I want to just have enough question for everybody. All right, so a point to you. Already practice that. And I said the reason that we have 1 over rho on the left rather than rho equals EI over M was we have one more equation added to the other end. And that's this. So this side is called large deflection. Now, 2 names, Euler, Bernoulli. You're going to see these names in other courses also, in math, in fluid dynamics, in other courses. Euler Bernoulli equation or model. So basically, if you're able to solve this equation, if you know the load, you know the moment, you know the material property E, you know the cross section, you know I, you solve this, then this D that you see is derivative. You have first derivative here, the regular derivative that you're used to in high school, and this is the second derivative. The first derivative gives a measure of slope. The second derivative gives us a measure of what, guys? You remember anything? The second derivative gives a measure of curvature. Curvature. All right. So, open question, guys. Some of you may have taken that course. I do not want to name it. What kind of equation is this? Yes, what's
Is that a differential equation?
what did you want to say?
I was going to say that.
Believe you and give you also a point. Yes, it's a differential equation. That's why you take that course. You should be able to solve the differential equation. However, this is a nonlinear differential equation because you have second order here, you have 3 halves here. It makes it really nonlinear and makes the equation not amenable to an exact solution. So whatever you learn there, it doesn't work here. It's too hard. And in fact, as part of my PhD, over 10 years ago, I was able to develop methods to solve this symbolically, numerically. So I wrote a couple papers on it. But the application was on compliant mechanisms. Mechanisms with flexible members. So those would really undergo significant deformation. So large deflection models had to be used for that case. But in this course, we're talking about solids. That's why mechanics of materials is also called solids. We're dealing with materials that would undergo infinitesimal deflection. So really sort of negligible or small. So in that sense, then really this could be approximated to 0. And it would collapse or simplify to the second order term only. So really the Euler-Bernoulli, the small deformation is this. As opposed to large deformation. So if you're able to come up with the load and the property of the material, geometry of the material, if you solve this, out of this we are able to find y, basically deflection at every point. So at this point, this is x, and this is a measure of deflection y. So that will give us a van. So in this course, we're not going to do any differential equation solution, but instead we're looking at 2 specific cases, cantilever and simply supported. These 2 geometries or these 2 loading cases. You have to solve this system and this system, basically for each case. This is called a boundary value problem. You may have seen these sets of equations given to you as homework in that course. The reason is this, because you need it in engineering. So this applies to everywhere, and these 2 points are basically what happens at this point, at this point, at this point. So once you solve this, out of this you get the solution. Again, this is linear, this is small deformation. What you learn there applies here. Once you do that, then you get the solution. Now you know at every x, you know the deformation y. So what we need in this course is the max deflection equation. You see that at x equals L, this is maximum. So set x equals L, and you will get y to be this value. So open question, guys. For an object, when you load it axially, whether you pull or push on it, we had an equation for delta, how much it deforms. Give me the equation for that, please.
Those are for bending?
Several hands, maybe alone. All right, Kiro, go for it.
Does it say force times length?
Just say the parameter, it's okay.
Yeah, force, PL divided by area times the modulus.
Modulus of
Elasticity.
elasticity.
I promise I was going to say the exact
I
same.
trust you, proceed.
About over 80. Yeah.
All right. At the same time, it was, I make it fair to you, hopefully this way. Wasi, Paul, and Kiro. Guys, really, to be fair to everybody, it's a hard job, really hard. Sometimes things are so interconnected that to make that decision whether it's fair or not is hard. So for instance, some of you had to be absent for a reason. And over the years I learned that for that particular reason, if you were able to bring me a letter, then I would give you basic excuse, right? If it's something else, I could not, unless you were able to give me a letter coming from an entity in school, or let's say health related, or any other thing when you attend a conference. That will make it fair. So that's why you have that policy. So really it's not whether I like you or not. I like all of you. I'm really interested in all of your success. But when it comes to be fair, I have to be all of you. So be mindful of it. So hopefully I made it fair to you this way. All right, so we said yes, FL over EA for this. As opposed to now for bending, that's FL cubed over 3EI. It gets more pronounced with the length when you push it in the lateral case, and you apply bending to it. So it's cubed in here. All right, so simply supported beam, it reminds us of our bridge project. So really that's max deflection for your bridge. If you're interested to include it, that's the equation for it. 5WL to the fourth, 384EI. In fact, once you're doing the project, you already have all the ingredients in. So just really plugging in and get that value. With another ingredient that you could add to your project. So we need these two equations. Make sure you put them in your equation sheet. And we want to do 2 examples, and that would be it really for this topic, really short topic. And if you want to take picture, please go for it. In machine design, you're going to need to do these equations. So again, simply supported, we call it because you have pin on one side, you have roller on the other side. You want to leave some leeway for the other point to move on. For bridges, for instance, to accommodate dimensional changes in different seasons, in particular this season. A lot of freezing, a lot of shortening, and in hotter seasons, for some elongation.
Compression, expansion,
All right, if you're done, let's do the first example. All right, Sander, I'll give you time. I'll start with you, okay? So the cantilever is given to us, the load is given to us, cross-sectional geometry is given to us. So you want to calculate how much deflection at point B. At point B, we know there's max deflection. Or Y max, delta max, doesn't matter really. In fact, Sander, out of the two cases, which geometry is it? You've not been taking notes. I saw that you were taking notes. You're not? All right, pay more attention, please, here. It's for you. Out of these two cases, Olivia, let him please take the point. But thank you for raising your hand. And out of these two cases, which one is that?
The set the bottom one.
The bottom one.
Yeah, so this is what it means.
Look at this. Look at the geometry. That's big. Which one is that?
For the first one.
You see that, right?
Yeah.
Now give me delta max for that. You just practice it. Just look at the screen and give me that. So Sander, everybody else, if you're in class, if you do not pay attention, you will not learn it. Oh, you need your glasses on. I see that. No. I see that he was not paying attention. It's just one big team. So please pay more attention, okay? Sander, we have two cases, cantilever beam for this geometry, you see? And this is single supported beam. We have two joints on the two ends. For this one, we need this equation. You see that? And for this one, we need this equation. So which one is this? Look at this. Which one is this? You said?
It's the first.
The first one. You call it?
Yeah.
Pronounce it, please. What is it?
The
Cantilever beam. Give me the equation for that. The max deflection.
This is the half hour of
Q, yes. 3 ER. So that's really the equation that we need for this. So give me the values, F. I want to pick on you so that you pay more attention, you learn more, okay? Give me the force value, please. 200, give me the length, please.
400 millimeters.
400. Just read it from there.
47.
For centi is 10 to,
10 times, or 3 times 10.
yeah, but centi is 10 to the power of
That's second.
negative second. All right, that's that. E value, please.
10 to
9. All right, thank you very much. I'll give you a point. I'll move on to Jansen. So please pay more attention, okay? Nothing else. And you should not be working on other things. Just pay attention. All right. So Jansen, And we practiced this bending a lot last time for the test review, right? X, Y, Z is given to us. The bending is about which axis?
Like,
Z, thank you so much. Very quickly. Then give me IZ equation.
base height over 12, and then your cube is going to be your y or your 3.
You said that, well done, well done. Well done. All right, so that's I. All right, calculate that and get a point. So Jansen, a point to you. Give me that in millimeter, please. Millimeter. Let's go with you.
9.48.
9.5 about, depending on how many digits of calculation you calculated those. Even much less. So confirm it, guys, against about trust. Please do that. Please do that. Yes, leave your hand up so I give you a point. Nathan Smith. Justin. Audrey. Leo. Ruth. Wasi. Audrey, yes, I did. Jacob. Tyler, Josiah, Paul, Reagan, and secretary, Hero, Ethan. Guys, when I compare you to the beginning of the class, I see that almost all of you are outperforming yourself. So well done, guys. Only through practice you get better. Aiden, Jansen, Dylan, Nick, Pax, Ray, Olivia, Gabe. All right, very good. So let's move on. Again, it's a short topic. Let's now do this comparison. The load magnitude is the same for the two. One is point load, the second one, the load intensity times the length, it gives you the same load. So we want to compare basically the two. We want to come up with a ratio of the deformations. I asked basically the first to the second, so let's do that. You know that the first one is free to move at point B, so it's got to be more. So delta top over delta bottom. We're interested in this. Because you're going to do calculation, let me work with Jack, and then I'll let you do calculation. So as a reminder, Jack, give us the delta equation, the max deflection equation for this. We know that it happens in here. Give me the equation for this. We just did that.
It's FL cubed over 3EX.
All right, and then give me the one for this. It happens right in the center here.
5WL to the 4th over 3B 4EI.
All right, very good. And we know that A over B over C over D, you multiply the farthest, and then put the numerator, and then you multiply the closest and put them in the denominator. So this is the same thing. We do that, this is FL cubed times 384 EI, and then 5WL4 times 3EI. And you can cancel this to get, or simplify this to get 128 F over 5 WL. So that's why I did not define any cross section, because the parameter I simply cancels out. All right, Jack, if you know the point. Yes, calculate this and get another point. So we have all the values given. F is 200, W is given as 500, length is 40, lambda negative 2. Again, because it's ratio, it's unitless. Go for it.
25.6.
That is. Again, I did this quickly with Jack so that you have more time with calculation. All C.
I also have a question.
Go for it.
How do we know which one will stop?
I will call this top, I will call this bottom, right? Jacob. Yeah. Evan. Olivia. Ada. Jansen. Pax. Justin, you were the first one. You guys, you have a question?
Yeah, I have a question. If we swap the order.
Do you mind? If
Oh,
I
yeah,
finish?
yeah.
Yes, thank you. Nick, Jesus, you said you
Yeah.
did it. Jesus, Augie, Sterling, and Dylan. Okay, Dylan, I did. Kiro, Josiah, Gray, Ethan, Gabe, yes, what was your question?
So if we swapped what was on top and what was on bottom, so we put the simple support beam up top, would we just take the inverse of that equation?
Yeah, if I ask, basically, I say, I moved in this direction 5 meters. One person would say, this person moved in this direction minus 5 meters. Yes.
Okay.
It depends on how you word it. Yes, of course, it would invert it if, had I said the second over the first. Yes, Max?
Yeah, does this value of deflection have like, or what are the units, I guess?
I just said that because we see two things, the same type, meter over meter,
So it's
it
just,
become unitless.
it's unitless?
Unitless. So as I said, this is really a short topic on deflection for beams. So from this point on, we'll be focusing on just one single topic for the remainder of the term. We're gonna do lots of examples on it. You're done with this? Any picture, anything, you're done? Olivia, I didn't give you a point?
No, you did, I was just saying,
Okay, thank you. Thank you for confirmation. All right, so, all right, yes, it looks daunting, but believe it, that I'm gonna make it look easy. So it's from chapters 7, 8, and 9. And different two approaches are given there. I put a little theory there to really connect it well. I will teach the two approaches simultaneously so that you're prepared for your machine design later or other courses that these equations show up. Once we connect it to what happens on the geometry side, then it makes really easy. It makes it really easy. So I know some of you have taken math programming with me, and I kept emphasizing there that as a programmer, we should be agnostic to the equation, the size of the equation. You should just care about what the inputs are, what the outputs are, and what connects the two. You should be able to do everything, even though you do not know the definition of any of the parameters. So it's the same thing in here. So I want to give you that sense. So make sure you have all of these. Again, these come from textbook, but you have to look them up. Different chapters, 7, 8, and 9. So it's all about stress transformation. So why do we need that? All right, so let me start with this. AJ, I remember, I promised you that we're gonna go over that. What kind of quantity stress is. We talked about it in my office, if you remember. So in high school, we learned scalars, being basically a number, the weight of a person, the length of an object. So these are scalar values, just one particular value associated to that quantity. And then we later generalized scalars to vectors. We said not only the magnitude matters, the direction also matters. You move in a particular direction, certain amount. All right, that makes it a vector. But stress is none of those. It's more than those. Yes, we kept talking about normal stress, shear stress, and in fact in one dimension. But in 3D, it's actually more intricate. Anybody knows, let's say, the third one? Let's say we have scalars, and then we have vectors. What is the third one? Anybody knows that? Yes? Matrix is a formatting of the data. I'll give you a point, but that's not that. So it is, yes.
I've heard of something called a phaser.
What was that?
Phaser?
Phaser. No, not phaser. Is it quantity type? Max, where do you learn it? Where do you learn it?
They just started talking about it in this too.
You said phaser.
Yeah.
Yeah, it's close to it. It sounds like that, maybe you misheard it. Because you most of the time have headphones on, maybe you misheard it. Anybody else? It's tensor. Facts? It's tensor. Close to that, right? Tensor. So, what is that? So it covers scalars, it covers vectors, but it does more. So what is that? So let me give you an example. The videos that we record on our phones, So the data structure for that. So if I geometrically talk about it, it puts layers on top of each other. On one layer, it puts different screens data. On another layer, it puts the color data. On another layer, it puts the sound data. So it makes it really layer by layer. It makes it, if you put more layers, you're giving it more, basically, dimension. We cannot visualize more than 3, but that's one way of abstractly talking about that. Guys, some of you are working on your own laptop, you're not paying attention, please. All right, so tensor, but you're able to format it in particular dimension, you're able to format it like a matrix. For us, stress is a tensor, but it's a 2x2 tensor, which can be formatted like a matrix that you see there. So let me zoom in on it. In a general case, sigma would look something like this. The main diagonal elements, you put the normal stress values on it, on different planes or axes. Let me switch to blue. And on the other, let's say, on the off diagonal elements, you put the shear stresses. So remember that the two off diagonal elements are equal and opposite. Equal and opposite. So really it makes it a 6-dimensional data set. 6D, not 6O. So 3 on the main diagonal and 3 on either off diagonal elements are independent. So if you know 6 unknowns, you know the stress at that point. And the subscripts X, Y, and Z, I mean the two subscripts basically say on which phase and in what direction those are being measured. So zoom back a little bit so that I have this. So if somebody asks you what is the stress at point Q, you put a cube like this along X, Y, Z, align it with X, Y, Z. You measure X sigma on that X phase, you call it sigma X, measure the 3 normal stresses, apply to those 3 phases. We know that normal means perpendicular in math. That's why these are perpendicular to those phases. And the taus are tangential stresses. Glues, for instance, they break tangentially. Those are used as joints. So that's why taus are shown tangentially on those planes, but they are pointing to each other or pointing away from each other, which is not shown in this case. They're pointing to each other to convey that these are equal and opposite. So that's the state of stress at a particular point in 3D. So only then, if we have all the 6 values, only then we say no stress at that point. All right. I see that you get used to it in this, you get exposed to it in this course, but you're going to see that in other courses. It's sort of related to my research topic. So I give a little bit more information just for your reference. In this course, in 3D, we're not going to do anything in 3D, but what does that mean? We're going to do a simplified version of this. So you have this object along X, Y, Z. For some application, you're going to need actually, let me switch back to red, you're going to need to transform the stress from one coordinate system to another. You're going to need it in this course, but it's in simpler dimension. What does that mean? This is the same cube oriented now about the red axes, the prime axes, which are distorted by these 3 angles or oriented with these 3 angles. Then if you have sigma, what is sigma prime? You pre and post multiply sigma by a rotation matrix, which is in terms of theta, phi, and psi, and that's a big set of equations. We're not going to do that, but for your information, this is what you would do in 3. And from this, you would get another matrix, but in terms of the primed coordinates, that's in 3. Why do we need to stress transform at all? I'll talk about that with example, but hold on to that for now. In particular, our focus will be on planar transformations. If you focus on this, planar basically means when all the elements is z or zeros, so no dependence on z. Where does it occur? Just look at these 2 sample applications. No matter what the magnitudes of these loads are, guys, if you're not paying attention, I will put absent for you. We're working on something else, not in this course. Please pay attention. No matter what happens in here, no matter how much load you apply here, it never goes sideways. So the 3rd dimension is really negligible. So really it represents a case like this. No matter how you load this case, the deformation here is really longitudinal, is minimal. So again, it makes it 2D. The 3rd dimension is 0. So for this case, it's not a 6-dimensional problem anymore. It's 3-dimensional. Remember that. Only these 3 are independent. The 3rd one are always equal and opposite. So in planar stress case, you're converting these 2. So that square is sort of collapsed in these 2 configurations, and only one angle is involved. X is rotated to x prime with the angle theta. Then what is this transformation? If I know sigma, what is sigma prime? And these are the equations that you would need. So I put it in zoomed in view because we're going to work with these equations over and over for the remainder of the term. So make sure you write these down correctly. Believe it or not, there were students that had typos there, even though we calculated that so many times. So we know sigma values on the right side of the equations. You know the theta. You solve for x prime, y prime quantities on the left side for planar stress case. That's the general meaning of it. And when we go over the example, I'll make it even clearer. To be able to work with these equations accurately, we have to have a convention for the sign of these parameters. So I want to give you some examples early on, just clarify the convention. Make sure you do write down convention so that you do not miss anything. For the test, you easily accumulate 10 points for that, or you easily lose 10 points. So pay attention, and then take those 10 points easy. Then how many of this do you finish?
Hmm?
How many of this do you finish?
3 or 4.
Very good for your body. I wish I could.
I know. What was you
I think, Jack, you responded, so it's Nathan's turn.
This is
I need more time to see some of yours still writing.
But you can make it happen. Yes.
How do we calculate tau xy?
I'm going to go over it now. Very good. I told you, I know you're rocking today. Very good. All right, so Nathan, we want to do practice on our convention. So sometimes the stress at the point is given to you, and then the goal is to put them on the diagram or the other way around. Okay? So I'll do the top left for you, and then you help me with the other one. Okay? And Ethan, I want you to do the bottom left, be prepared for it, and Greg, I want you to be prepared for the bottom right. Okay? So top left, I'll do that. So the convention for sigmas is the same as before. When you see that positive, you put it outward. You're pulling on that face. If it's negative, you put it on the inward direction. Guys, phones aside, please. So sigma x, I see that as positive. So on the x direction, put it outward for the 2. Again, whether to the right or the left, no. Pulling is positive, as before. Push is negative, as before. So this is 10 megapascal. Whether I put the value on the right or left doesn't matter. Put it on one of them. All right, now sigma y I see is negative, so put it inward for the 2. And put the value either on top or bottom, but do not replicate or repeat the negative sign, because by putting the arrow inward, you indicated that to be negative. So be mindful of that. In the test, if you put negative 40, that means it's incorrect. Negative 40 in that direction means positive 40 in the other direction. All right, so that's that. This part was repeated. You already went over that in legs 1 and 2. But tau, just follow this. Because there are 2 ways. To be more accurate, see how this particular one, just this one, look at this one. I just circle it. Look at this one. How this creates moment about the center. If it's positive, it has to be counterclockwise, peristatics. Counterclockwise should be positive. So if it is counterclockwise, it's positive, put it upward. So put this one upward, or easier, if this one is upward, it's positive, if it's downward, it's negative. The first one is more accurate, but the second one, just you find it that way easier. How do you figure out the direction of the other 3? Well, once you figure out this one, for the object to be in equilibrium, this one has to come to it. The other 2 have to be opposite of those 2. As easy as that. We're going to do these 3 examples together. All right, Nathan, help me with this.
So for the top right one,
Yes, please.
so it looks like there's a lot of compression going on.
So on this one, you said it's compression. What's the value?
Yeah, so I think that the negative 45 is, that's compressed.
Yeah, what's the value I should put in here?
Say again?
What's the value that I have to put in here?
instead of negative 45.
I just said that, I just emphasized it. When you put an inward, you put the absolute value there.
Okay, yeah, all right. That makes sense.
All right.
So-
And then here,
So top and bottom, I think you're gonna have 30 MPa pushing in. as well.
very good. All right. And then negative 10 goes where?
So,
You always look at which one?
um,
For tau?
for tau, so do you start with the, that's in regards to the arrow?
Yes.
The
Yes.
direction of movement.
Yes.
Um,
Always look at this one, you see, always look at this one.
the top right. Oh, yeah.
Yes, that's tangential one, this one.
Because on a coordinate system, the top right is always,
Yeah, so here the convention is this, always look at this one, literally, always look at this. If it's upward, positive, otherwise negative, so what should I do with this?
I think that one's gonna be going, that's gonna go down.
Yes.
Than the other side.
All right, what about these other three, what about the direction of this?
I think they're gonna continue the clockwise direction movement.
So this one,
Yeah,
goes to right or left?
I think it's gonna go left.
But I just said it, you were not listening? Look at this comes to it. This is this, it comes to it. This is this one comes to it. So it has to be to the right. That's the convention, you're just looking at it, just convention, just follow that, okay? And the other two have to be,
Well, the opposites.
Opposite.
Have to
that's it,
compare.
that's it. And the value of it is,
Wouldn't that be the 10 MPa?
very good. So you could put it on any of the four corners, okay? It says the same thing. So really that's convention. Okay, Nathan?
Yeah, makes sense.
A point to you. All right, Ethan, help me with finishing this up, and I'll give you as usual time to write it down. Ethan, help me with the values now. We're doing the other way around. Emphasize the sign if it's positive. Sigma x,
Is negative
negative what?
1.
Sigma y,
It is positive 10.
tau xy.
Is negative 45.
Ethan, everybody else, however you did it to come up with this, make sure you document it in your notes, equation sheet, so that you do not miss it, okay? Well done. All right, Jack, I'm sorry, Ray, please.
Yeah, sigma x is 8, positive 8. Sigma y is negative 17. And tau is positive 14.
That's it, very good. So all of those equations really depend on these. So Josiah, you see we're working in that direction. Tau is this way, either it's given to you, or, or you have to figure it out on the diagram. All right, all agree. And Leo, I want you to also help me with 2 more examples after this. I want to make sure everybody is done with the writing. Because that will be quick, let's do those and then we'll take a break. All right, so we're not gonna do the whole problem now, but you help me with these values that I want to extract. We know that all tau xy is negative tau xy, so we do not care about the third one. But please give me these 3 values out of this diagram and emphasize the sign. Sigma x is,
Oh, sorry, no, it's positive 120.
all right, sigma y.
And then sigma y is negative 60.
Why did you say negative?
This one, oh, it's positive, sorry, this one now.
So up or down doesn't matter, just pulling or pushing, please, pay attention. You don't want to miss any points. These are easy, get all the points. All right, tau x, y,
And that would be positive 120, or 45.
45. All right, a point to you. Leo, be prepared for the next one. So we're going to get back to this to finish up the example, but we have to learn the other equations. Again, we'll get back to these, but Leo, please help me with this. All right, help me please with values, emphasize the sign.
Sigma x is positive 16 megapascals. Sigma y is negative 48 megapascals. And tau xy is negative 16 megapascals.
That's it. Point to you. All right, we get the break now. Please come back by 11:27. And I'm texting and walking is Elon.
So,
Yeah, I understand. Okay, so
You always look at this one. This all board.
oh, okay.
So we know that one, right? What happened with the other three? One of these come to us, the other two the opposite. So here, this one comes to us.
Okay, so in this scenario here, there's no stress happening.
These are shear stresses. This, even though we acknowledge that we're talking about 1 point,
Okay.
right?
Okay.
We zoomed in on this point, what's the stress there? And we cube there, we measure the stress in this direction. This direction.
I see.
In this direction, these are sigmas, x, y, z.
Okay.
And then how much they rotate or distort will be the tau values.
Okay. And then with this one, it's just positive because the odds are because it's on the it's just
Yes, you always, even though all of these four have the same magnitude, but the sign on this x, y, this one is x, y. This one is actually y, x.
okay.
But you don't need that.
Oh, the
So this is negative 45. Why this? It's always negative, you see. Tau y x equals negative tau x y.
okay. So
is equal and opposite to tau xy. Yeah, that's good. And the equations of these are always equal and opposite. If one is positive, the other is negative.
And then if this one's negative, this one will be positive.
Or not. But what do you need to do like that? Just erase this portion? But it is okay. Tau 1x, tau sub 1, sub x equals tau negative tau xy. If it is positive, negative, positive comes from you.
I see. Okay, so in this tau x would just be positive 60. Okay, all right, thank you.
Aiden, are you always tidy at home?
I try to be.
Yes.
This is. So you guys have so it's listening. Because that's not waiting anymore. And also, I'm pretty sure it's not including your tests. It's including all the.
And you have the choice.
Thank you. Well, the homework's barely affected your grade anyway, so you just got me. We have a feeling.
Average out the weight to like your standard car.
Yeah. I don't remember Tyler.
No, this was right.
Yeah, he's the other group member. So I found, this is just public data.
There's one getting.
This is just data on the bridge, the Sunset Drive. That's what the bridge is called.
Yeah.
It's not University. But we have all this. Their span links right here.
We're looking at
Number of lanes, highway pedestrian, waterway, concrete box beam, girders. Then you have the total length of maximum span, which is 15.8 meters, and structure length is 62.8 meters.
X and Y.
And then you have your operating rating, some methods. That's operating rating 6, which is
3.7, 37.3 metric
I'm trying to
tons.
remember. That isn't max. That isn't max load though.
Yeah, I figured that's pretty low for a bridge.
Yeah, because it's not a
Because it's 4
it's not a
lanes.
semi. It's not a semi. Like a 18-wheeler bridge. They don't. So it doesn't need to meet 18-wheeler standards.
All right.
So because an 18-wheeler can be 70 tons easily. So
The only things that I can't do are the schedule. Other than that, everything's fine.
So it's the deck structure of the concrete cast in place. So that's important to know because the bridge is from 1957 and was built in 1957. Now, now we have better concrete technology now. So I can go back and I can find the original mixture of the concrete because that's open. That's just data we have what the average concrete usage was used during that time. We can get the maximum compressive force that can take before it goes kablooey, and that could be helpful. I don't know.
Do you mind creating in Gmail? You can make a chat. And
Yeah,
you
I
can,
did that
Okay.
already.
Awesome.
We did that.
Awesome.
So I thought we were doing the Chevy Avenue one side. I did.
That's fine.
Yeah.
All right. Thank you.
All right, guys, we want to do 2 examples for today. This and the next one, and as soon as we finish, then we could leave. All right, so let's do this one. I'll give you time to continue writing.
Bless you.
Bless you. Tax, did you answer? It's your turn. I'll give you time. I'll let you know. I'll let you know. Let's get there. Guys, this is the easiest, per the records. This is the easiest leg of the course. Even though the equations look hard, but really the easiest. And with this example, you're going to get the crux of the idea. All right, so if I may have your attention, if you understand that, the remainder of the term we're going to have easy time. So my point of contact is PAX at this point. So this stress that you see is the input stress. So if you look at our garment, if you look closely, you see that they're made of fibers, right? Pattern in different orientations. So suppose I'm pulling on it in this direction, that's sigma x that you see there. And pull in this direction, then that's sigma y that you see there. And then somehow I was able to exert shear on it. That's not easy, but that's 3D. It's just an example. Suppose I was able to put shear on it. All right, I was able to make a twist. All right. The question is this. The fiber that you see with 70 degrees oriented in that way, what stresses does it get? You see that? Is that a valid question?
Stress?
Yes, stress. It is stress. It's all about stress, isn't it? So, did you understand the question? So a fiber we're putting the stress into the system, into the garment, what happens to a particular fiber, all right? So sigmas that you see on this side, these are input stresses, and this one that you want to calculate is the fiber stress. So the prime values are the fibers. The non-prime are the input ones. And the theta is the angle or orientation of the fiber. But remember that with this convention, x to x prime is theta. Now, Pax, these are the equations that we need. But look here, it says, statement is asking us for this. It says, give me the normal and shear stresses on this fiber. You see that? On this fiber, if this is x, this is x. If this is the fiber, then this is x prime. The angle that I need is this angle, this physical angle, this theta. I need. And the stress on this, let me switch to a different color. On this, if you go back in here, just look here, this was sigma x, this was tau xy on that face, right? Now the oblique face or that fiber is this. The stresses are that are on that is sigma x prime and tau x prime y prime. See that? Sigma y prime is happening on another face. So on this fiber, I need sigma x prime, tau x prime, y prime. You see these equations? These are all of the equations. Had I asked you for the stress on this, you would have also needed to have this middle one. But for now, we need sigma x prime, tau x prime, y prime. You have them written?
Yeah.
All right, then give me, so I really need, I didn't give any gesture to this, I just, what happened?
You have to press the X.
Where?
Top screen, all in top, just the X.
Do you see any X there?
Yeah.
Oh, okay,
Yeah.
thank you.
Mhm.
Because Jesus was first to say that, let me reward you with a point. All right, so this is
Jesus.
sigma x prime. Again, it's sigma x prime, you want to avoid repetition, so you go for sigma x prime. And this is the shear stress on that, tau x prime, y prime. So when it says normal on that face, really this is sigma x prime. When it says shear on that, this is tau x prime, y prime. So then, I want you to give me the big equation for sigma x prime, and I want AJ to give me the other one. Yes, say it, once you're ready.
Normal force or sigma average
Sigma
plus
average,
sigma x minus sigma y over 2 times cosine 2 theta plus shear xy stress.
tau xy,
Or tau.
tau xy.
Sine 2 theta.
Very good. So point to you. Before I forget, let me do that right now. All right, next one, please.
Okay, so, tau x prime, y prime is equal to negative sigma x minus sigma y over 2, multiplied by sine of 2 theta, plus tau xy cosine of 2 theta.
All right, AJ point. Now be prepared, get 2 points for the 2. But we need so the sigma, taus, we already have them up there. The theta, let's just clarify that value first. AJ point. Next, okay. Radian, theta by definition is this angle between x and x prime, which is this, right? A measure of angle is given for the fiber with respect to horizontal axis. You see, this is 70, but I need this. This is 70, what do you think this is?
Is that also 70?
So if you look by comparison, do you think it's closer to this or this? So it's a geometrical question. Look at this. This is theta, right? And if we draw that one, the 70 degrees is also horizontal, and this is 70, right? We know that. What is this angle?
110,
Now, if this is 70, what is that?
70,
If this is 70, what is this?
oh, 20,
20. All right, let's do this. If this is 20, what is this?
20,
If this is 20, what is this?
70,
This one is
20.
20. All right, the theta is 20. Now the catch is this: in your calculator, make sure you put in the right setting, 20 degrees. So sigma x 120, and leave everything in mega. The result will be mega. You do not have to convert it. Do not overcomplicate it. Gabe, give me the equation for sigma average.
Yes. Sigma average equals sigma x plus sigma y over 2.
And Gabe, for that very reason, it's called average.
Yes.
You see
Times
that?
2.
Exactly. Add them, divide by 2. So this is sigma x plus sigma y over 2. All right, Gabe, I gave you your point. So now you have all the values. Once you have both values, the first person that gave me either one gets 2 points. And everybody else gets the first person. Yeah. Jacob, how many of these do you have?
I got the first one. So.
Okay, go for it. What's the value?
I got 84.
That's off. That's off. Next one. Make sure you have it in the right setting. So we're practicing this for that reason. Degrees is degrees. If you have your calculator in I don't know who was first. Do you know who was first?
Yeah, that's fine.
What
No,
did
no, they can add, it's okay.
I don't
go
care.
for it? Go for it.
All right, 141.91.
What did you find?
I got 128.37.
That he got the point. That's correct. 141.90 megapascal. But confirm it now. Get 1 point for it. Just think it's 2 points.
They can have one.
I'm sorry.
They can have one.
I'm sorry.
Oh, I was gonna give one to them.
No, but she didn't get the correct value.
Oh, okay.
Yes, she has to confirm it, and then give it. I saw who first or the second one.
Yeah,
Well-
not for the second one, sorry, I was confirming one for.
So let's now confirm the second one. Let's get the second one, so I see who gets the 2 points. So I'm asking you to come up with the value of the second one first now. Go for it instead.
10 point.
That's off. Okay, yeah.
15.18.
You got it.
1 ounce.
All right. Now from this point on, confirm both when you raise your hand. Make sure you have both. So Jake get 2 points.
Yeah, I forgot a minus sign.
And then Jacob, did you get the first one?
Yeah, I put a minus instead of a plus right before.
All right, I give you point for that, so that I'm done with you, and then just are you confirming the first, the other one basically?
Yeah.
I'll give you a point for that, then I'm done with you also. So from this point on, everybody please, when you raise your hand, that is you're confirming both. The more 2 points. Aidan 2 points. Gabe 2 points. Reagan 2 points. Audrey 2 points. Guys, please do that. We're doing this for you, so let's keep our honesty. Kiro 2 points. Tyler
Signal. How did I get signal? Yeah.
2 points. AJ 2 points. Pax
I know, man. Thank you.
Evan. Olivia.
Sorry.
Leo. Sturdy. Ray. Ethan. So you were able to calculate stress on a particular fiber, Josiah. So let's do a suppose question. It goes to the next person who was, I think Olivia, it's your turn, isn't it? And after game, right?
I was,
There's one, sorry, it's Olivia. All right, Olivia, let's do the suppose question. So actually first an open question. What is the objective of this course?
Just to be able to critically discuss the safety of.
Yes, what's that? Comment on the safety of the object or the system under consideration. Nathan Smith. Now, when we want to say comment on it, not only we're able to say, if it's safe, the factor of safety that we calculate, it tells us that it's above 1, and we know it's safe. Now, if it's not safe, we could also tell in what direction or on what fiber it fails. Is that really strong? On what fiber it fails? It's really strong, isn't it? In what orientation it's going to fail. So, another open question. If the object is made of a brittle material, when you torque it, how will it fail? Brittle material, you torque it.
It would twist. I'm not sure how to describe it. It would just.
It would break apart at 45 degree angle.
45.
That's
At 45. At 45. You're breaking it. Let it break it. Cool. Just looking at it again.
breaking it.
All right, yes, at 45 degrees, right? So in fact, now with these calculations, next class, I believe, we're going to get to that point, or actually today, next example, we're able to calculate that 45 degree angle. It could be arbitrary. For torque, it's easy, but even for something complicated like this, we're able to calculate that. All right, now, going back to Olivia. Olivia, suppose the material is made of so it's made such that tensile strength is 150 megapascal and tau u is made of 12 megapascal. So is that safe and why?
No, because your tensile is above what the safety rating is, or above the allowable. Your tau.
Taking which one?
Your tau is above what the allowable is.
Yes, tau is not sigma, correct. So this is the strength, this is the max that it can take, where you're giving it 15.19, so not safe. And this one is greater than 1.90, this is safe, but overall, again, one failure, too many, not safe. All right, go to Olivia. So the fiber is not safe. The angle was given to us, the fiber was defined, but sometimes not defined. We have to figure out which fiber is most critical. So in fact, we were able to do that. So this example, we're done. We're able to calculate the two stresses. All right, any questions on this? All right, let's do, okay, I'll let you take a picture. Let's do the last one for today. Something like this you're going to see on the last homework. Yes.
Is there going to be a sigma X and sigma Y in the same problem, or is it just going to be one or the other?
Then sigma y prime.
Yeah, one prime, yeah.
Yeah, so I think I went over that here. So really it's about the wording there. So this phase, you see, the stresses were on that. And then we're looking at this fiber, we rotated by theta. So really these two are converge into this. Sigma y prime is not there. It's on another fiber. I did not ask for it. All right, so let's do the last one for today. So I said there are two approaches. One is graphical. It's named after the person who developed it. It has its own advantages. And as the person's name is Moore, H perhaps, I heard that to be silent. I mean, it was silent. How did I clear that? Yeah, people normally pronounce it as silent. Moore. We want to do the two basically together, related to. And as I said, in machine design, you're going to need this. All right, Raiden. You stayed away from it. Yeah, please be prepared for this. I'll get there. I'll give some definitions first. when you're writing this down, student of mine previously was able to crack a joke on this, maybe a little bit too detailed to get it on the first run. I'll do my best. I'm just paraphrasing it somehow. The person was asked, are you able to solve the plane stress problem
Plane stress problem.
or elasticity problem? He said yes. He said, what do you need to be able to solve a lot of plane stress problems? He said, give me more circles. Give me more circles. M-O-R-E. When he said, I laughed.
I don't get it. Solve the plane's problem.
Thanks, Olivia, for helping. Thanks for being nice to me. All right, Breda. You want to combine the two approaches. First, it literally says draw the Mohr circle. What is that? I want to go over that. I want to do a warm-up first. This is x, y coordinate system. All right? This length, suppose is 3, and suppose this is 2. This is the point A. Give me, please, the coordinates of point A. And guys, please pay attention because this applies to you in this, let's say, more complicated scenario. But I want to say it's as easy as this. So look at this, point A. Give me the coordinates of A in this coordinate system, please.
2, 3.
So do you start with Y?
3.
Isn't that? So you normally say X and then Y, all right? Is that 3, 2? All right, let me switch this. What if I put Y here?
Negative.
Which one is negative?
Is the y positive?
Yeah, if I put it there, that means in that direction is positive. You're correct. Just go for it, repeat it.
Negative 3.
No. Negative 3. Again. Give me X coordinate. What's the X coordinate? 3. What's the Y coordinate?
3, negative
3, negative 2. So we want to do the same thing. So the convention here is you put sigma on horizontal axis and put tau underneath on y axis. All right? We're good? Convention. That's how the math works for this problem, for this topic. The textbook says put tau on top, but with one flaw. It says take clockwise to be positive, which is not consistent with what we did in statics or other things in this course. So put it underneath. All right, that's the convention. Sigma to the right is positive, tau downward is positive. All right, now, as a GPS, help me. This is the coordinate of that point. Let's call this X point. Let's call this Y point. Now, Braden, as a GPS, help me. I'm at the origin. Tell me go to right, left, up, down, this much. And then get me to point X.
So we're going to have to go 60 on the strain, or the stress axis.
All right.
And you're going to have to go, it's going to be above the
Right.
stress axis, 60.
60. Well said. So I'm here. That's point X. All right. I'm back at origin. Help me with the other points.
So you're going to have one on the left side,
Yeah, how much?
48.
48. Somewhere here, okay. And then, we know this opposite, so that's 60.
So that'll be just
put down that.
I'm sorry, up or down?
Need down.
Down. Very good, very good. So that's point one. So as easy as that. Just follow this convention. We're getting there. We want to draw the circle. Right in a point. So if you draw it to scale, then the circle will look good. All right, you want to draw the circle connected to where it crosses the horizontal axis, called that sigma average. And it is because it's in the middle of x and y. On the x-axis, so that's why sigma sub-average. That's why we have that equation. So I'm connecting it to the equation that we have there. So sigma average. So Tyler, now give me the value of sigma average in this case. What would you do to get sigma average?
Sigma x minus sigma plus sigma y,
All right, please, yeah, that's correct. Give me the values now.
16 plus negative 48 divided by 2.
Well said, well said. You said plus and then minus 48. Well said, that's the way to do, so that we do not mess up the signs. I don't mind with the numbers. The procedure is fine. So as negative 16. Tyler point. So again, this is, now from this point on, this is the center of the circle. Sigma average is the center. So do your best. With this as the center, sigma average as the center, draw a circle that crosses x and y. Something like this. This is more of a lemon than a circle, right? I did my best. So, circle with sigma average as the center, crosses x and y. That's more circle. All right. So what? Yes, there are some big points about this circle. Evan, let's have study of this particular circle. As a review, we know that if you move to the right, sigma increases. To the left, decreases. If you go down, tau increases, right? Now you tell me where on the circle sigma is maximum.
Magnitude wise?
Yeah, just no, just do not worry about the sign. Do not worry, include the sign. Where is maximum?
All the way to the right.
All the way to the right. So mark this as sigma max. Where is it minimum?
All the way to the left.
All the way to the left. So we're connecting little by little. The computation approach should be the graphical approach. Now, look at sigma average. First of all, where is tau maximum?
All the way down.
All the way down, right below sigma average. Or did they give you a point? equal to WASI. Now, WASI. Where, just look at the point where tau is maximum. What did I say? Average, tau max. Look at where tau is maximum on the circle. Give me the sigma coordinate for that. What's the label? Sigma coordinate for the point where tau is maximum.
Oh, sorry, sigma average.
Sigma average, well said. What's the point? So that could be a quick question time for the test. So where tau is maximum, sigma is average. So really here, max shear stress, that's tau max that we are after. The corresponding normal stress, that's sigma average. And principal stresses are, in this course, are referred to sigma max and sigma min. What's your question? Okay. If we now go back, I see some of you already. You want to go back to the theory slide? Actually, we can do this and then go back there and confirm. Actually, Drew, we are at the center, right? One of the specifications of the circle, one is center, the other one is
Radius.
radius. So what's the radius of circle in here, in this case?
The radius would be calculated as, if we're using just the points on there, we find it as sigma max minus sigma average.
Divided by? Oh, you said it. You said sigma average. That's correct. Or look vertically. What else can I say?
We also say that it's, that could be calculated as, tau max times 2. Or
That would be the average. Tau max. So you were able to drive it for us. I point to you. Let's move on to Cole. Cole, if you're at sigma average, if I give you sigma average, what would you do to get to sigma max? Say it.
I'm working on it. It would just be tau max and one, because it would be
If you have sigma average, you want to get to here, what should you do? What is that? What is this length?
the radius,
If you're here, what do you do to get to there?
sigma average is tau max.
You said it. And Drew just said that it's the radius, right?
Yeah.
All right. As easy as that. Josiah, you're at sigma average. What would you do? What would you do to get to sigma min?
You take the average minus tau
You
max.
said it. You said it. Going to you as well. So if we go back to our theory slide, actually I need a little space here. Tau max. Okay, I do invert it. If we go back to our theory slide, we see that these equations are there. So it's here, let's look here. So we're able to connect the two. These are principal stresses. You guys derived that for me. And tau max is also given here. All right? So really the computation approach, the one that we did, was easy to each other. All right, Nathan. Nathan, help me with the values, please. Give me please the equation, remind us, tau max. You don't have it? You forgot?
Yeah.
All right, write it down from here. Guys, be prepared for it. I want you to calculate it for me. Tau max calculator. You have it? Say that out.
Square root of, in parentheses, sigma x minus sigma y over 2, all that squared, plus tau x1 squared.
All right, point to you. You have the sigma values on top, use those. Make sure you put the right sign for any of those. The result will be mega. And let me put the value and then you guys confirm it, please. 68. All right, Jacob and Justin. Josiah. Jesus. Drew. Reagan. Jansen. Audrey. Leo. Ethan. Kiro. Wesley. Cole.
Not actually confirming the number, I'm just a little confused on something, so with,
I'm sorry?
I'm just a little confused on something, so with, tau is y in positive in the equation, but ours being negative, when I put it in, I just get an error for non-real answer.
I see, but did you put this entire thing squared or not?
Yeah, it should be 60 squared.
It doesn't matter, you just put 60 squared, right? Minus squared or positive squared, it's the same thing, right? Bring it here. Are you fine or not? Bring it here. Yeah. Olivia. Aidan.
Yep.
Sturdy. Evan.
I see. You do put, if you put all of this in parentheses,
Did that,
it just says,
Nick.
in the calculator, you have this 48 square. So if you square the whole thing, you should get
The whole?
Yeah, plus, yes, because it says plus is the sign. How is negative, so you have to do parentheses around that. But because it's going to be squared, it's the same thing. Great. Then I did give you. All right, so then plug those into here. You already did that. I already did these, but these are easy ones. Let me put the values for you. 52 megapascal. And negative 84 megapascal.
Yeah, it's the same.
So all those terms we did.
You can just put you can this one. You can calculate this.
Taking one question.
No.
And these one are easy ones, yeah. No points for these. I will get the points for these. Justin, you have a question?
Oh, no, it's the same. Yeah, it's the same.
Nathan, you confirming that one?
Thank you, Justin.
All right, so now the good part is this one. Draw the principal state with reference to the initial state. What does that mean? All right, let me go over that. So, use green. This state on this segment that you see that connects sigma min to sigma max on the Moore circle is the principal state on the Moore circle. And this one, I don't know what color. All right, I don't know what is the name of this color. Little orange brown. So this one that we started with is the initial state on the Moore circle. And the angle between the two is twice theta sub p because it represents principal. So how much should you basically rotate one to get to the other one as twice that angle? Why twice? That's how the math works. If you look at the big sigma x prime equation, all of those equations have the twice theta in the arguments for sine or cosine. So as twice the theta, how far you should rotate to get to the other state on more circle. But this does not tell us anything in practice. What does that mean is this. I want to say basically what fibers on this are principally loaded or critically loaded. How far should I rotate from this initial configuration? This is the initial state, right, that I see. It's loaded. What is the fiber? What is that angle that I have to calculate? That angle is calculated through the formula here. This is the angle. That's our tangent angle. Tangent inverse angle. We write it down. This P stands for principal. That's principal angle that we would need. As shown in here, we're going to replicate this for that example. This is initial state. And this is principal state. This is in physical domain. So you want to do the physical domain. Yes?
Is the angle you draw on the circle, is it 2p or 2 theta or theta?
On the circle, 2 times theta sub p.
Okay.
Yes. But in this scenario, in the physical, is 1 theta p.
Okay.
And that 2 was because of this. Just look here, because of this 2.
Oh, okay.
All right, we have about 8 minutes. Just let's finish that off. So let's put that equation here. So I continue in here. So theta p is 1/2 arc tangent of twice tau xy. Now the sign of tau matters in here. Let me actually switch to red, so that's more visible. So if you put the value then from your calculator, you would get negative 30.96 degrees. What this means is this was our x direction. When it says it's negative, that means it's clockwise. Go clockwise about this orientation. Separate that angle, 30.96 degrees. Draw that square or cube, basically collapse form in here. This is initial state. And this is, you want to fill this up, complete this. This is principal state. Now let me switch to blue. On this, remember, tau equals 0. No tangential stress. And there is a reason for that. On this, you only need to put sigma max and sigma min. Which one is sigma max, which one is sigma min matters. The textbook says do through computation, but I'll show you a quick way to figure that out. No tangential one. That's why I did not put any tangential arrow on that. So, can I have your attention? Can I have your attention? I said one of either this or this is sigma max. The other one is sigma min. Pay attention here. Look here. This is the initial one, right? Look at x. Always look at x point. Is it easier to rotate to sigma max, or is it easier to rotate to sigma min? Who was the next person? Yes, thank you, just go for it.
Easier to rotate the sigma max.
And say this one is, what you said, it's that one. Sigma max you said. Put sigma max on this,
Sigma max on the right.
on the horizontal.
Yeah.
And we found that to be 52. So as positive, right? You learn that convention is positive, you put it like that, pull it with 52 megapascal. The other one is the remaining one. If this is sigma max, the other one is sigma min then. We found negative 84, so you have to put it negative, put it inward, and put the value to be positive, 84 megapascal. So this is principal state. Just an approach. So basically that means this. If you load the system like this, let me switch to green, the fibers along this and along this are critically loaded in the same orientation as this. So these are critical fibers. One is loaded, critically loaded in terms of tensile stress, the other one in terms of compressive stress. And the theta is defining that angle. Had you started with torque alone, you would have gotten that 45 degrees. So I think that was a good example, and we're going to do more next class. And we have a long weekend ahead of us, and you guys enjoy that, guys.